Our second presenter is Chidong Zhang. Chidong leads the Ocean Climate Research Division at NOAA PMEL, where he has been since 2016 after 20 years as a professor at the University of Miami. His research has emphasized tropical atmospheric and climate dynamics with an emphasis on subseasonal variability and the MJO, as well as their interactions with ENSO. His talk will focus on observing the ocean-atmosphere transition zone.
Thank you. Thank you for this opportunity for me to introduce you probably not very new concept, the ocean atmosphere transition zone. So this workshop has, during the past more than 2 days, we have discussed how to use the current capabilities to observe the tropical Pacific Ocean to fill the gap in our knowledge, understanding, and modeling and prediction. In my talk, I want to take you beyond the Pacific and beyond the tropics, and maybe beyond the field campaign that we are trying to figure out what to do, to the 10 years range, basically to think a little bit broader. I'll explain what I mean by that. But the discussion of this work so far pretty much covered a lot of materials I have prepared. So I can go very, very fast. I don't have to go into many details because it's already covered. And I don't think I have difficulty to convince you that this concept of ocean atmosphere transition zone is something that we need to think about. So before I go on, I want to acknowledge input to this presentation from Shui Chen, Chidong Zhang, and Carolyn Reynolds. So the essence of my presentation basically is ask one question: what should our observing capabilities for Earth interaction be in 10 years from now? Okay, we're thinking about a decade later. Well, during this workshop, we have a lot of brilliant ideas of what we want to do. I'm not going to repeat that. This is just a short list, and you can add many things from the discussion at this workshop. But no matter what we want to observe, it has to be based on science and based on the need for modeling and prediction. It's not just because we want to observe that. So what would be the science driver for future observation requirement? Again, here just list some of the things I thought of, and this workshop has come up with many, many other things that can be added to these slides. One example, and we have been discussed through this workshop, is we want to resolve smaller scale Earth interaction features, and we want to understand the cross-scale Earth interaction, and so on and so forth. So I'll just go through. I won't go through this list, and go to the next slide, which is what the requirement from forecast and modeling perspective. Again, at this workshop, we have discussed many of them. I just list some of them, and one example is, for example, most of the coupled models does not include wind wave current interaction, and some models that do demonstrate this is very important, and what observations we would need to help advance the coupled models to include this capability. The other one is we discussed the freshwater input into ocean model and produce this we call the fresh jet. And as we know, most ocean models does not include precipitation as part of their upper ocean salinity budget. So what kind of observations we need to help to advance ocean model in that perspective? And there's many, many examples. So I'm not going to go through these details. Given those science and forecast modeling drivers, how do we advance our observing capabilities? So here comes with one idea that there's a plan to form a 1-year study team on this subject, on future observing capabilities for Earth interaction. The background of this plan is that there has been discussions among the US agencies on R&D of Earth system predictability. And there is a working group represented by NASA, NOAA, NSF, ONR, and DOE, specifically discuss the need of advanced capability of observing Earth interaction. And this working group come up with these suggestions. Why not we have a one-year study team and organized by the US CLIVAR office and supported by one full-time administrative staff. Start probably fall of this year, and 1 year later, submit a report to the US CLIVAR office. And the report basically answered the question that listed on the top. What should our observing capability for Earth interaction be in 10 years from now, and how should we get there? So the specific objective of this one-year study team are given here. It's a little bit wordy. They mean to cover as broad perspective as possible. So I'm not going to read through everything. The essence is this study team should summarize our current capability, the key gaps, lesson learned from the past, and what's the best way to move forward, and what we should more efficiently use whatever data we have to advance understanding, to advance coupled data simulation and prediction, and how to balance the cost and societal benefit, right? And you can consider this one-year study team as a mini decadal survey if you are familiar with the NASA decadal survey. And this is on a smaller scale. And the chart you can consider is just to come up with a roadmap to future observing capability for Earth interaction. This team will not start from scratch. The community already start thinking in this way. We are already thinking in the future, and these slides just show some examples, and there's many of them. And this one-year study team will build upon existing ideas and try to synthesize them. There is a problem in our current practice of study Earth interaction. For example, if you are an oceanographer, what you do, you start from the surface down. You include all the upper ocean studies, and that's the example showing on the left. If you're an atmosphere scientist, what you do, you start from the ocean surface going up, and that's the example showing in the diagram to the right. Very few published studies consider the vertical profiles of the ocean and atmosphere simultaneously. And this is just one example. And I challenge you to find other examples in the literature, and please let them know if you do have. So this raised an issue that we consider Earth interaction not including both atmosphere and ocean together, as we discussed at this workshop. And this workshop has provided so many arguments, convincing arguments, that we need to consider both upper ocean and atmosphere boundary layer. But in practice, we only do them separately. So I'm going to propose a provocative idea that we need to redefine Earth interaction. At this current stage, when we mention Earth interaction, our thinking immediately zoom into the sea surface, right? But this workshop has repeatedly called upon our attention to be paid in upper ocean and the atmosphere boundary layer. So the Earth interaction should not be defined at the air-sea interface. It should be defined through the entire ocean-atmosphere transition zone. That is the upper ocean, air-sea interface, and atmosphere boundary layer as a single identity, not as a sum of the three components. What do you call it? You can call it transition zone, transition layers, coupling zone, continuum, whatever, it does not matter. The essence is we have to put atmosphere, boundary layer, upper ocean together and think that's where Earth interaction takes place. And this is very important, especially for our next generation of scientists, because in the future, we want to study Earth's interaction with the ocean and atmosphere together. So in their definition of Earth's interaction, they should automatically include in this transition zone, not just the focused air-sea interface. And you probably have seen similar figures as this one. It's just trying to pile in as many as possible the features in the upper ocean at the air-sea interface in atmosphere boundary layer that are relevant to air-sea interaction. And this is basically my illustration of the transition zone. The problem is the following. What is our current capability to observe this transition zone as a single identity? In that case, we need to observe the transition zone simultaneously at a single location, right? And ship measurement is our gold standard. We have a ship, we can equip it with all different modern sensors and equipment, and we can observe almost everything we want in the atmosphere, in the ocean, and at the surface. But this is only at a single point and during a short period of time because of the cost. Now, airplane can give us a spatial gradient and is mobile and is adaptable. But it has its own limitation because a lot of essential variables we want to observe, especially in the future, we cannot. For example, turbulence and many other things.
Sorry to cut in here. 3 minutes left.
Okay, so what do we go from here? Now, think broadly, think widely. We can collect all the existing observing assets, put them together, and that probably will give us the observation need for the transition zone. And we can develop a single supersize that can observe both the atmosphere boundary layer using laser or microwave radiometer. And maybe we can add a platform that our aerodrome can land and recharge. So we have the capability to observe the atmosphere profiles, or maybe even more crazy, and we can design a robotic cormorant that can go into the water and stay on the surface and fly in the air. There's many possibilities. So by the end, this one-year study team is charged to think broadly, out of the box, and come up with ideas what our future observing capability of Earth's interaction should be, right? In the next step, maybe we can form a one-year workshop to discuss how to how to form this one-year study, or maybe we can do that online. We have not decided. The current thought is this one-year team should be very diverse and inclusive, representing the three sectors: the government, academia, and private sectors. Should be balanced by professionals at various career stage, balance between science, technology, and should focus on observations, but motivated by coupled data simulation, coupled modeling and prediction. And it should leverage with the current activities such as Ocean Decades, NASA Decadal Survey, and NOAA Precipitation Prediction Grand Challenge, and other existing review and advocacy papers. And probably the membership will be 10 to 15 to be manageable, maybe include ex-officio members from the agencies. And the big question is what the selection mechanism. So I propose this idea to you, and I hope I can collect some information from you, suggestion, comments, and to move forward. I'm looking forward to work with you on this one-year study team. That's it. Thank you.
Thank you, Chidong. Great talk. There's been a number of references to your request for more details or more papers or studies on showing both the atmosphere and the ocean boundary layers. I'll just skip over that, but you can see it in the chat. So going to a question from Simon and a related question from Billy, so I'll do them together. And the comment is that the relevant scales of the phenomena, and hence the observations that are needed on the different sides of the air-sea interface, are different. And Billy says, not everything needs to be observed everywhere all the time. There's a role for focused, shorter-term research observations. We have these different mix of tools we can use with, satellites doing uniform sampling and models that interpolate between sparse and in situ observations. And so he's asking what's the right mix of these tools. And I want to flip that, link that back to the previous question that, the possibly being different scales that are relevant in the two spaces.
Well, I think there is two approaches. One is take advantage of current observing capabilities, right? We have so many different assets, how to put them together, use them effectively and efficiently. That's what we're doing at this workshop. This one-year study team is to look beyond this. 10 years from now, are we going to use the same tools? What new tools we need that we don't have now? And how do we develop those tools? That's what this one-year study team is charged for.
So do you have any comment about the sort of relevant, significance that the different scales in the two, in the atmosphere and the ocean being, I guess, the platforms we have obviously take into account of this, like ships, but I don't know if you had any.
Oh yeah, the scale is different, but if you're talking about mixing, right? You need a turbulence measurement from both atmosphere and ocean. So there's commonality, and the atmosphere have convection and precipitation that you don't have in the ocean. So definitely there's a variety of different requirement from atmosphere and ocean. So the challenge is how do we best observe both atmosphere and ocean effectively and satisfy the need for advancing our understanding and the coupled data simulation and prediction.